So I'm going to talk about Apache ZooKeeper. So we're going to start off with a little thing. We're going to have a mission. And our mission is to build a distributed lock service. So let's say that you have some kind of thing, whatever resource that may be, that you have different processes, maybe from different computers that are going to connect to it and do stuff with it, and they all need to use it exclusively, right? So you need to build a distributed lock so that only one process can own that lock at the same time. You need to preserve the ordering for whatever reason, because generally you want to do that. And you need to ensure the lock gets released if, for example, if one of the clients dies or something like that, one of the processes dies. OK, so it did actually self-destruct. So first, let's do a little bit of training, all right? So ZooKeeper is termed as something as a distributed coordination service. And the way that it does that is it's a distributed hierarchical file system. So it's like a file system just on your machine, whatever machine you have, except for a tablet, which I guess doesn't really expose any file systems, but your Mac or your PC, except that it's distributed across a cluster of machines. Okay, so that provides you high availability and fault tolerance, because if one of those machines dies, it doesn't wipe out everything. You just basically fix a machine or put a new one back in. It's fast. Okay, and the reason it's fast is because all of the reads of the file system are coming from in memory. Okay, so obviously that's going to be faster than if it's reading from disk. And the last thing it does is that it facilitates loose coupling. And so, for example, if you have this lock service that we're talking about building later on, different clients of this lock service really shouldn't have to care about each other. They shouldn't even have to know about each other existing. And so one of the things that ZooKeeper does is allow you to build systems like that. So has anybody heard of the fallacies of distributed computing? Okay, so number one is that the network is reliable. And if you worked on the project that I work on, you would know that the network is definitely not reliable. We have stuff go down all the time. We're like, what's going on? Oh, HDFS, we can't reach it from one place to another. And so it's not reliable. Okay, so that is something you have to deal with. One thing is partial failure. Let's say that you have a client and it sends a message to some other machine. And then the network dies before you get a response. Did it succeed? How do you know? Because maybe it succeeded, but the response just didn't get back to you. Or maybe it died, and so you don't know that. So you have to actually reconnect and figure it out and ask, say, did this actually happen? So partial failure is something that you have to deal with when you're dealing with distributed computing. And ZooKeeper handles that scenario. The way that it does that, in large part, is through this sort of follow the leader architecture. You have leaders and followers. A leader machine is elected by the followers, a group of followers. Once that machine becomes the leader, all the followers connect to it, synchronize with it, the state of the distributed file system. But the trade-off that you get there is that the followers may lag the leader. They may not always be up to date. So if client A is connecting to server 1 and client B is connected to server 2, client A may actually see different data than client B, because, let's say, server 1 might be ahead of server 2 in following the leader. So you have to be aware of this eventual consistency model. So what are some of the problems or some of the scenarios that would solve? So one thing is group membership. And there are various things like HBase, which I'll talk about in my lightning talk later, actually has it's a distributed database across a cluster of machines, and it needs to know, well, what machines are actually online at any given time. Blur, which is near infinity's blur, also is a clustered distributed search. And so at any given time, you need to know what is online and what's offline. So ZooKeeper can be used for that sort of group membership stuff. You can build distributed data structures like locks and queues and barriers and all that, and things like that, using the primitives that ZooKeeper provides. You can build a configuration service. So let's say you had a cluster of machines and you wanted your configuration for all of those machines, because maybe it's just not web apps, but it's other standalone apps that are connecting to this configuration that need to know the overall configuration of your system. You could use ZooKeeper for something like that. Okay, so let's do a little training exercise. So let's see how you would build a group membership application. So the first thing you have to do is get connected, okay, to ZooKeeper. So as a client, you have to connect to ZooKeeper, and then a session will be started. This being Java, it's going to be extremely verbose and ceremonious, and we're not going to worry about that. So connect. Okay, so I've written a little connect method here. I'll come back to the countdown last and why that's there. So Create a ZooKeeper. ZooKeeper ZK equals new ZooKeeper. We pass it the host. This is basically going to be a string that consists of all of the different servers in your cluster, okay, of ZooKeeper. You're going to give it a session timeout, and then you're going to give it something called a watcher. Okay, and that watcher is going to watch for events. And the reason you have to do this, and then so you create that, so nothing's actually executed. You just have an object, right? And then you await using this countdown latch. And you say, why do you do that? Well, you do that because for whatever reason, and I don't really think this is a great thing to do. In fact, I don't think it's a good thing to do at all. When this constructor actually starts a background thread to connect to ZooKeeper. So if you don't wait for it, you might not actually be connected and have a session yet. So that's why the countdown latch is there. You await that. When you get notified, when you get called back by the watcher, which is watching for the connection events, you count that latch down, it releases the lock, and you return ZooKeeper, and you're done, and you're connected. So that's kind of annoying. You can encapsulate this kind of stuff in a helper class to not have to do this, all over the place. So I mentioned sessions. So when you do a connection, a connection is established, and then a session is created. And the sessions has things like timeout, so you might, as you might expect. But one of the things that's cool about ZooKeeper is that it automatically fails over. So if you're connected to a machine, if you as a client are connected to some machine up here in the cluster, and that machine dies, ZooKeeper will take note of that, and it will automatically migrate that session over to another machine. Without you having to do anything or even necessarily knowing about it, you'll still have the same session ID. You'll still have the same view of the ZooKeeper system and the distributed file system that you did before. So that's something that it preserves. The hierarchical file system is composed of things called Z nodes. And they can be either persistent or ephemeral. We'll talk about what those are a little bit later. Well, I guess basically persistent means it stays around beyond the length of a client. Ephemeral means if a client goes away that created that ephemeral node, that node goes away as well. Optionally, you can have sequential numbering on either of those types. So you could say, if you want to create a queue, then you might imagine that I need to know the order of things so that I want to preserve the order of people who are in the queue. And interestingly, it can hold data like a file, but it can also have children. Z-nodes can also have children. So think of a directory that has data plus children. Okay? So in our group membership, what we're going to do, the first thing we're going to do is we're going to create that group. We're going to create the group Z-node. And so it's fairly simple. You get yourself a group name. Everything is absolute paths in ZooKeeper, so there's no relative paths, so you always need to start with a slash. And so you can just say, OK, I'm assuming we have a ZooKeeper object here, and say create the path. You can pass it some data if you want. In this case, it's null. You can pass it an ACL for security if you want to, and then the create mode. Should this be persistent or not? So for our node that holds the group members, that needs to be persistent. So we'll create it as persistent. Join, if you note going back and forth, is pretty much almost identical. And I probably could have factored out the code better, but I just wanted to show that it is pretty much identical, except for the fact that I'm going to create it as ephemeral, and the path is slightly different, right? Because I'm going to be a member in / group name / member. So / group / node 1 / group / node 2. So that's joining a group. Listing a group, you can simply call get children. In this case, zk.getChildren. The false over here is basically saying, I don't need a watch on this. I don't need to set a watch on this, so don't bother calling me back whenever changes occur to that node. Okay? And we'll just loop through and do that. So at the end of our group, let's say we're shutting down our server. Maybe what we want to do is we want to delete that node. So then we can just delete. And so deletes, remember Steve earlier when he was talking about couch said it's optimistic locking. ZooKeeper is normally. But it also allows you to pass -1, which says unconditionally delete this. I don't care what the version is. Although one of the things you note is I have to do this nonsense first because it doesn't recursively delete parent nodes. So if you want to delete, you have to actually go down to all the children and delete them first. And so you can imagine that would be really tedious. But so right now I'm just deleting the children, and then I'm deleting the parent. Okay? All right, so at this point, I'm going to switch over and show you. Let's see, is this running? OK, so ZooKeeper has a server called Quorum Peer Main, and I'm going to then start up something called ZooInspector. And this is a little GUI client that's kind of ugly, but it lets you see the nodes in your ZooKeeper cluster. I'm going to connect. I'm not actually running in clustered mode. I'm just running a single node on my machine. I'm going to connect to that, and here I go. I have the parent nodes, and I can expand and see, okay, I've got different things under there. So I'm going to go back here and come over to this tab, and I have a bunch of scripts that basically just call Java programs, the same calling the code that I just sort of demonstrated. So the first thing we're going to do is we're going to go ahead and create a group. Okay, so it just went ahead and created a group. I come back over here, refresh that tree, and you can see that sample nodes was created. So I'm going to place a watch on that, and all that's going to do in this app is it's going to put up little growl notifications that say, or its own version of growl, that say, hey, I've got stuff happen to me, my node's changed. So the next thing I'm going to do is I'm going to create a whole bunch of stuff at once. I'm going to join, I think there's like 5 nodes that are going to join. So I'm going to run that, and a whole bunch of stuff's going to happen. And then if I'm going to come back over here, you can see all that stuff going away, because if I refresh this, now I've got 5 nodes. Okay, so as long as these processes, these client processes are there, these nodes will stay around. So for example, if we do find the things that are there, so I'm just using JPS, and here you're seeing that, oh, look, those are all the programs that were launched. So let's kill one of them. Let's kill 37310. So kill 37310. Okay, so if I do that, that was one of them, right? Did it? OK, hold on. Oh, it went away. I guess I missed the notification up there. So if I do that, that's cool. So I can then, oh, sorry, that's already done. So if I want to, I can join other things. I can say join group, node, put that back. Did I kill node 3? Node 4, I put that back in there. I can put 6 back in there. I can put 7 back in there. And I'm getting all those sort of change events on the right-hand side. I guess that's, and so if I refresh this, it doesn't auto-refresh. But you get the idea. So this is a way that different apps like HBase or like Blur or like whatever needs to do this can know what clients are there. So I'm just going to go ahead and kill all of them now. So we'll see all of them, just a whole bunch of stuff probably. I guess it's only going to show 1, and then if I refresh that, they're all gone. And then just to finish it off, I can go ahead and delete that group. And node deleted, so it's gone. So that's pretty simple, actually, to build a group membership application that's distributed across a whole cluster of machines with just a little bit of code. OK. Oh, come on. All right. So I talked about some of the architecture and design behind ZooKeeper, but we'll go into a little bit more detail now. So first thing is the data model, which we already talked about. It's a hierarchical file system. As I mentioned, Z-nodes can have data. But as this is not a distributed database, it's more for coordination and stuff like that. You're limited to a megabyte of data, and usually you're going to be storing a couple of kilobytes in there. You're not going to be storing a whole lot if you're actually storing data in there. In the group membership example, where we had just the nodes, we didn't need any data because just the presence or absence of a node was what determined the behavior. So I mentioned watchers, and we sort of saw how that happened. So write events in ZooKeeper trigger watchers whenever read operations are called. So if somebody sets a watch on the get children operation, anytime other clients are adding children or deleting children or whatever, then that watch gets triggered. And we'll talk a little bit more about watchers later. Another thing about ZooKeeper is that it is atomic. So you will never read a partial state. You will either completely fail or completely succeed. Same with writes. Writes are atomic. And I mentioned security with ACLs, and you can basically put ACLs on Z nodes for restricting people, but the security is not really industrial strength, although it is pluggable. I'm not really going to focus too much on it. I mentioned the different types, but what I didn't probably make clear is that you can have, these are 4 different types. So you can have persistent and ephemeral nodes, and then you can have persistent sequential and ephemeral sequential nodes. And both of the ephemeral types will die as a process died. So in the group membership, when I killed that process, that ephemeral node went away. So the node 4 went away. For things like queues, and as we'll see in the lock example later, you can have sequence numbers appended to them. So in this case, the node names would be x dash, and this is like the ZooKeeper session ID, and then this stuff on the end, the zeros, all those zeros, those are the sequence numbers that are maintained by ZooKeeper itself, and you don't have to worry about. But what it does guarantee, it guarantees sequence and ordering. Okay, so it makes sure that there will never be that it only hands out 1, 2, and 1, 3, and 1, 4. You won't ever have a situation where two clients see the same number. And so that way you can preserve ordering across the entire ZooKeeper system. So these are the different types of operations. There's basically read operations and write operations, and they're pretty simple. They're CRUD. So those are the primitives that it provides. Create, delete, exists, get children, get and set data, get and set ACL, and sync. Sync is interesting. Basically what it does is, as I said earlier, followers can lag the leader. So if a client says, you know what, I have to have the most up-to-date data, it can call sync. And that will force that follower to catch up to the leader. And no operations will continue until that is caught up. And if it can't catch up, then basically the session will be migrated to another node automatically, so that where you can get that. So the examples so far were the synchronous APIs. I call something, I wait for a result, I do something with that result. But there's also an asynchronous API as well, if you want to. So synchronous, this is an example of synchronous where we're just basically doing something. This is the list example. I call get children, I wait, so essentially this blocks, and then I do something with the children. Well, if you can do other work while it's getting you this data, then you could use the asynchronous API. And so in this case, it's still get children, but it's just an overloaded method. So we're going to set the path, but we don't need a watcher. And then this async callback, children callback stuff, and all of these have like a process result method with various methods or parameters. So they have the return code, the path that was operated on, an optional contextual object. And in this case, it's children because specifically we're looking at get children. If it were like exist, then you get a stat object back, which basically, like if you know the stat command in Unix, it tells you information about the file or the directory you're looking at. And so get children, then I can pass this null here. That I can pass a context object in there. If I passed an object in there, say a map or whatever, then that's what would be passed to me when this gets called back into the process result. And then I could figure, if I needed additional information, for example, to figure out what the context was, what did what, and to make decisions on whatever I needed to do. So there's an async API if you need it. So watchers, one of the things about watchers is that they're one-time events. So when you get notified of a watch event, if you have to re-register if you want another one. So you have to keep watching. If you only want one time, you're good to go. But if you want to keep going, you have to reset a watch. David.
Could you miss an event if you fail to re-watch one time?
I'm not talking about that yet. Yes, the answer is yes, but I'll talk about that in a second. So that was Dave's point, was that you can miss updates. And so we'll see that, I think, on the next slide, actually. No, maybe not, in a couple slides. Okay? So all of those write operations that we saw, they are the ones, when write operations occur, they will trigger watches to fire on read operations that registered for them. So think of it as a pub-sub sort of architecture, if you will. So the watcher interface basically has one method. It's pretty simple, although it does have a bunch of constants for the types of events, because that's a bunch of enums and sub-enums and weird stuff. Like they have interfaces inside an interface and an enum inside the inner interface, and I'm like, what are you guys doing? But whatever. I guess it goes to Brian's complexity point. Maybe they like fetishize over the complexity or something. I don't know. So that's the watcher interface. Here's some complexity. Okay, so let's say that what we want to do is we want to watch child Z nodes as they change. And we want to keep watching them and keep watching them and keep watching them. So this is one way you could do it. So you could have a method called watch children, and I'm going to acquire initial semaphore that has one permit. Okay, so that basically means I have that right now because the first time it's called, I have that on my watcher. Then I'm just going to loop forever. Okay, and when I do this, the first thing I'm going to do is I'm going to say, hey, get me the children and pass this in. This is the child Z node watcher. You see up there in orange on the upper right, it says implements watcher. So I'm going to pass myself in, so I'm the one who's going to get called back. And here I'm overriding the process event. And basically what I do is I say, when something has happened, so the only time I'm going to get notified as if that node has changed. If a child's been added or a child's been deleted, I'm going to get called back. And when I get called back, the only thing I need to do is release that semaphore, because that semaphore is going to make sure that I can keep going. I guess I should have said, you get the children, you display them, for example, and then you try and acquire. So at this point, you're blocking. You're blocking right here because I've already acquired it up here. And then when I get called back, I release the semaphore, comes back to the top, gets the children again, displays them again, and blocks until the next event. So in that way, you can use asynchronous callbacks to receive events and just keep it like that, almost like a main loop in a GUI program or something like that in Swing. The main event loop is what I was trying to say. So this is what Dave was talking about when you're using watchers. Between the time that you get notified and the time that you re-register, yes, you could miss events, especially if you have a large bunch of servers and there's a lot of operations going on at the same time. You could actually miss those updates, and so you have to sort of be aware of that. If that's not tolerable, you're going to have to do something else, because there's no way to guarantee that you will see every single update. What you will see, you'll never see things out of order. You might miss a couple of updates, but you'll always see things in order. So be aware of that. Gotcha. Cool. This next slide is on data consistency. It's for Stephen, whose favorite quote is this by Ralph Waldo Emerson: "A foolish consistency is a hobgoblin of little minds, adored by little statesmen and philosophers and divines. With consistency, a great soul has simply nothing to do." So think about just why you do things. Why do you do things? Do you do things consistently just because you've always done them that way, or because there's a specific reason to do them? So in ZooKeeper, consistency has ZooKeeper guarantees different things about consistency. So first, it guarantees sequential updates. It guarantees that if a client sends in a number of updates, those updates will be applied in that order and no other order. It guarantees durability of writes. If the write's been persisted to ZooKeeper, it's durable. It's there. Atomicity, as I said earlier, it's all or nothing. It either happens or it doesn't. You have a consistent client view across all servers. So what that means is that in the case of a failover or something like that, I as the client will never see a different view. I will always see my view. So if I am connected to a server, that server dies, I pick up with another server, I will only see to the point where I was at. I'm not going to jump ahead and lose things and stuff like that. And then eventual consistency. If a follower machine is lagging, then ZooKeeper will terminate it and migrate the session somewhere else. So I keep saying cluster and ensemble and these various things. That what ZooKeeper actually calls it is as an ensemble. So I found this is kind of a cool picture. It's from 1921 jazzing band on Wikipedia. I thought it was a pretty cool picture. But so a ZooKeeper ensemble pretty much looks like this in terms of the architecture. So you have leader and you have followers. And what happens is, so you have all the clients on the bottom. The clients are doing various read and write operations. So all the reads are satisfied by either the followers or the leader, and they're all satisfied in memory. Okay. When writes occur, they go from a client to a follower, whatever follower they're connected to. And then the follower forwards that write to the leader, because all the writes go through the leader. And then the leader broadcasts those changes back out to the followers, which is why, as you can imagine, if this broadcast happens, that's why the followers can lag, because maybe they're busy doing stuff and they're not going to be necessarily all at the same point. Okay. So how do you get this leader? So when you first start up a cluster, the other thing to note about this slide is that there's an odd number of machines, because all of these operations in leader election and when you're persisting writes, it has to be a majority. Okay. So when I'm doing leader election, I have to have a majority of the machines in the ensemble basically agree that, hey, this guy's a leader. And when I'm doing writes, or when a leader broadcasts, it will not return success to the client until a majority of the followers have all said, yeah, I'm good to go. I've got it. Okay, so majority rules. Clients have a session on one server. I talked about that. Automatic failover. I guess I talked about those too. Although I do want to keep pointing out that the reads are always satisfied in memory. So again, this is not a distributed database that's massive scale like HBase or something like that. It's more for really fast coordination across a bunch of machines. So clients actually can ask for a specific timeout period, which is kind of unusual. And then what will happen is ZooKeeper will negotiate that. So if you ask for a timeout period of like 10 seconds, it might give it to you, or it might say, no, I'm going to give you 6 seconds. So it's up to that. Sessions have an automatic keep alive. So if you have a client that's just sitting there doing nothing, which is what the group membership example would do, then what happens is the ZooKeeper client will automatically send ping requests every so often to make sure that your session stays alive, session stays alive, session stays alive. And that's why, and so basically there's a lag time. That's why if I killed that group node, I might see a delay between when I kill it and when everybody else knows about it. It's in ZooInspector, as was happening actually earlier. So rights, we talked about the first 2 points. Global ordering. So there's a global ordering of updates through the entire system. So you can have tons of clients all doing stuff to ZooKeeper, to the distributed file system, but the order will be the order in which operations are applied or the order in which they are received. You won't see things out of order, because ZooKeeper gives every transaction a ZX ID, a unique global transaction ID. No, actually, it doesn't go based on clock time. If you are storing data in there that has clock time, then yes. But otherwise, it doesn't need that.
If 2 clients, try to write data to 2 different followers, not the leader, how do they?
Well, each client is connected to its own specific.
Right. But I mean, will a given client's actions always be in sequence, but not necessarily? Like if 2 clients are doing things, how do I know that if?
Because all writes go through the leader. So the leader is the ultimate dictator, and it knows the order in which things are received.
That isn't finished until it's
Yeah.
agreed.
Yeah.
So I guess you block until your write's finished.
Yep. Mm-hmm. Yes, Chrissy.
It seems like the leader is a point of failure. Is there an emergency backup leader? I mean, what happens?
Oh, good point. Yeah, I guess if the leader dies or the leader just stops responding, there will be a new vote. A new vote will occur, and a new leader will be elected.
Now you have an easy number.
That's true. Yeah. But so you can survive up to two nodes dying if you have that. Oh wow, I'm like going to be way late. All right, so I'm going to keep going. So there should have been a category called most late. I think there was a category for the thing that said most on time. I'm going to be most late. Okay, so our final mission is creating craft. Okay, distributed lock. All right. So again, we want to do mutual exclusion between processes and decouple our lock users. So what we're going to do is we're going to use a parent lock Z node, okay, and then we're going to have ephemeral sequential child nodes, and that's how we're going to build our lock. So the idea is going to look like this. So we're going to have a sample lock. Process 1 is going to come in. It's going to get the lock. Process 2 is going to come in. It's not got the lock because process 1 is still doing something. Process 3 comes in. It still doesn't have the lock either yet because process 1 still has it. So let's say process 1 is done. It goes away. Now we want process 2 to automatically get the lock. Okay? So process 2 goes away. Process 3 is going to automatically get the lock. Thank you. I'm going to be late, so it doesn't matter. And then we're done. Okay, so that's what we want to do. So the basic algorithm is like this. Create a child ephemeral sequential node in that parent node. List the children of the parent lock node and set a watch on that. If the Z node from step 1 has the lowest number, then you've acquired the lock and you can be done. If not, then you have to wait for that watch event you set in step 2, and you have to go, when you get a watch event, you go back to step 2 and figure out the children again and figure, am I the lowest number, and do I have the lock? If not, you keep repeating until you get it. But there are problems with this. So Apollo 13, like a main B bus undervolt, as I was reading last night. So connection loss, the partial failure thing that I talked about earlier. What if somebody is trying to create that child node and you have a partial network failure? How do you know whether you actually created it or not? So what you can do to solve that is you can embed the session ID in the child Z node names. Because if you remember, we had that X dash and that whole blob of numbers and then a dash and the sequence number. That blob of numbers in the center there was the session ID. So that way, if there's a connection loss, that client, when it reconnects, will basically say, hey, I just need to find the children and find out whether or not there is a node that happens to have my session ID in it. If there is, okay, then I can proceed. I know I created it. Otherwise, if there's not, the creation failed, and I got to create it, and then I can proceed. So that's problem one. Problem two is called the herd effect. So you could have a whole bunch of clients watching this lock node, right? What's going to happen when one of those child nodes goes away? Anyone? Anyone? Gift card in it for you. That's right. Everybody's notified. Oh, you want Subway or Potbelly? Oh, I definitely want to throw at him. So yeah, so you get a whole bunch of things, and potentially, if you get a spike in network traffic, if you have a lot of stuff going on. If you don't have a couple machines, it doesn't probably matter. But in the general case, you could have that problem. So the solution to that is that you'd want to set a watch only on the preceding node. So if I've got like process 3, I only want to watch process 2, and when it goes away, I've got the lock. But you might say, well, what if the process right before me dies? Okay, well, if that happens, you would simply watch lock 7. Because it doesn't have to be the immediately preceding number, just the immediately preceding alive child node. Does that make sense?
Does that happen automatically?
Yes. Well, yeah, the code's got to check that, right? So it's got to keep checking that. So every time you get a watch, you can't just assume that you have the lock necessarily. You have to then check all these different conditions again because of all the things that could happen. Like if I was lock 9 and I was watching lock 8, if I was watching lock 8 and lock 8 dies and it goes away, I get notified of a change. Then I go and look for that, and I don't find it. But what I did find is I found lock 7. Lock 7 is still there. So now I'm going to say, oh, I don't have the lock. I'm going to watch lock 7 because that's the one that's preceding me now. Brian.
And when you go to register to watch lock 8, what if it released the lock during that time? You'd be watching something that no longer has a lock, right?
Yeah, but you'd still get notified because remember the global ordering and the atomicity, you'd still get notified. You get notified of all of those things. All right, so implementation, are we going to do it ourselves? No. We're going to be lazy and we're going to use existing ones that they already have in ZooKeeper. I'm not quite sure. I guess they don't put them in the main ZooKeeper distribution. They put them in a recipes folder. So they provide a write lock and a lock listener. So the write lock, and this is all asynchronous, so the write lock calls back to you when the lock is acquired. Okay. So one of the things I said, for this, what I wanted to do is I wanted to actually have you be able to write code that says, like, create a lock, lock it, do stuff, unlock it. So I wanted to make it actually synchronous. So how could I do this? I could take the Apache write lock and create a blocking write lock. And again, I'm going to use a countdown latch. On creation, I'm going to create some stuff, create my write lock. And it's basically as simple as this. When somebody calls lock, I'm gonna call lock, and this is an asynchronous method, so it's going to return immediately. I'm then going to call await on the countdown latch. Okay, unlock just literally calls unlock. The second piece of this puzzle is in this sync lock listener implements lock listener. So it's an inner class, and it's on the next page. And what it does is whenever it gets notified that the lock has been acquired via the lock acquired method, it's going to count down on that latch. And when that happens, then this will stop blocking, and you can go do stuff. Do whatever you need to do. And when you're done, then you call unlock. So you might imagine some code that looks like this. I have a try block. I say lock. I do some work. I catch an exception. I unlock it. But that's easy to forget. So you don't want to do that. What you want to do is something like this. You want to create maybe the distributed operation executor because it's Java, and we have to have verbose long names. So we're going to create a with lock method that takes a distributed operation, which also in Java has got to be an interface instead of just a closure. So I create my lock. Then this is basically then a template method, right? So I say lock, return the result of executing that operation, and then I unlock. And so now I can ensure that if I call with lock, that I'm never going to forget to do an unlock. So, and this is just an example of using it. So executor with lock, do distributed operation, do stuff, and then I'm ensured that the lock gets appropriately opened. I get the lock, then I can do stuff, and then I can release it. I'm not going to, well, all right. I'm already late, so it doesn't really matter anymore. So I'm just going to go ahead and run it. No, it doesn't, because I'm going for, and if you want the beer later, you better, All right, so I'm going to start up this thing called Lock Watcher. Lock Watcher. Okay, so what this does, it basically says, okay, I'm going to keep watching who has the lock. So no one has the lock at the moment. So I have this thing called what is it called? Oh, run bunch of workers. So this is basically going to launch a whole bunch of stuff all at once in the background. And I should start seeing a bunch of stuff. So on that, you can see a whole bunch of stuff. Q is attempting. So what I basically did is I created processes A through Z, and each one of them is trying to acquire the order, or acquire the lock to do stuff. Now note that it's not actually in order necessarily, because I launched them all at once in the background, and it's just locks are acquiring things as they go. And so what this is doing is it's basically just showing you what the current lock nodes are. And every time somebody releases it, so X is doing some work, and so on and so forth, you'll see this go down by 1. And we're not going to sit here and wait for that to happen, but it'll just keep going. OK, so mission accomplished. All right, so review. I'm not going to tell you the review. You're going to tell me what I just told you. And we have some nice beers that you will get to choose from that I picked out at Whole Foods today of varying varieties. I have 6 of them. All right. Who wants a beer?
There's a talk on ZooKeeper. Good enough?
No. I think I saw Jeff's hand. No, that doesn't count either. OK, who's next? Nobody wants a beer? The question is, we're crowdsourcing the review. I'm not doing the review. You're doing the review, and you get beers if you point out good points.
You store small data, less than a meg in your...
That's true. OK. You want to come and choose? Or all right. What's that? Nodes can have data. OK. And can ephemeral nodes have children? No, but you can have, but you can have a beer anyway. All right, who's next? Steven. What? You can miss updates. All right, come on up and get a beer. Mike.
But updates will always be in order.
That's true. All right, come on. It's John.
It's all in memory, so you can't really store a lot of data.
What's in memory?
The node.
That's right, the whole file system. All right, come on up. How many more do we have here? This is a queue. This is a distributed queue, I guess. All right, I think you already asked. You already got a reward. You don't get anything, Matt. Eventual consistency, but you can call sync if you want to make sure that that client's view is up to date. All right, so I guess you get the last one. All right.
Bring it to me. Excellent.
All right. Cool. So that's it. I'm done, and only less than 10 minutes late. So as I said, I win the latest category. We need to change the review form. All right. Anyway, thanks.